Hello everybody, welcome back to another final exam example video. That's a real mouthful. I'm going to get tired of saying that, but it is what it is. In this final exam example video, we're going to be covering the 2013 final question 2. Now this question in particular is a very simple question where all it's really asking for is the shear diagram and the bending moment diagram. I always want to say bending shear diagram, but again that makes no sense at all. Now if we look at the beam, it's actually not too bad to determine. It has some loads on it, but nothing too crazy. But as we're going to see, there's going to be a little trick to this question. And unfortunately, if you don't get the trick, everything goes wrong immediately. And that is having to deal with all the hinges in the beam. So if we were to actually look at this beam, member BD, as we can see, has a hinge. So it's connected through two hinges. Oops, I was on black. Let's go to red. As we can see, we have two hinges for member BD. And if we were to look at member DC, well, it's also connected by two hinges. And as we're going to see, it's going to come into play a little bit later on. It's not going to be too complex, but unfortunately, if you don't know the secret, it's not going to be a good time for you. That was unfortunately my case because, as many of you know, the 2013 midterm and finals, those were mine. So I hold these ones really close to my heart with a lot of hatred, if I'm being honest. But it's okay now. Looking back, I realize that it was probably my fault. But we won't tell the faculty that. Alright, so if we're to look at this question, it says, in figure 2, beam ABC is supported by a pin at A and a roller at B. Beam ABC, member BD, and member CD are pinned together. So basically hinges. And then of course it says, note that the member thickness can be neglected. Now the first part of the question, part A, says determine the reaction forces at A and B. So even though it doesn't specifically ask, what they're going to mark you on, first of all, is going to be a free body diagram. So that's where we're going to start off. I'm just going to scroll down. I'm going to say, okay, we're going to start off with part A here. And the first thing I really want to do is draw a free body diagram of the beam. So I'm going to switch over to black. As we can see, the majority of the beam is just a nice straight line. I say nice straight line, but then my iPad doesn't correct me. Okay, let's say something like that. We can see that we basically have kind of a rectangle, yeah, it's more of a rectangle, on the right-hand side of the beam. So I'll try to do this as nice as possible. I'm not an artist. I can't even say the word. And neither are you guys. So as I'm drawing this, always keep in mind that the faculty does not ever expect you to have beautiful diagrams. It would be nice if you did, but we're not going to mark you on how beautiful they are. So as we can see, we have the majority of the components. We have the beam itself. We have the two support reactions. And I'm just going to go through and start adding all of the loads. So at point D at the very top here, we know that we have a load, a lateral load of 40 kilonewtons. So I'm just going to put 40 kilonewtons. We can see that we have two distributed loads, and I'm going to do those in a second. Kind of at A here, we have a concentrated moment. So I'm just going to put this here, and we know it's 20 kilonewtons per meter. Kilonewton meters. And then of course we have support reactions. So A is A is a pin, meaning that we're going to have two support reactions, one vertical and one horizontal. Again, we are just going to assume directions. So I'm going to leave it as follows for now, and you can label them whatever you want. I personally just go AX as well as AY. And then at B, we have a roller, so we know that we are going to have that vertical reaction, which I'm just going to call BY. Now the last thing that I need to add, of course, are my distributed loads. And the reason why I did it last is because a lot of students ask me, Clayton, how do I put a distributed load in a diagram? Well, I'm going to show you what I do, but there really is no wrong answer as long as it's clear to the marker what exactly you did. So what I like to do is I like to represent it as a dashed line. So I'm going to have something like this. In the first one, we have a nice rectangle. So I represent it as a dashed line to kind of show it's a distributed load. And then in a solid line, I'll put my force. So we know that this right here, I'm going to call this force F1. So I'll just shade it in, and we'll call this one F1. We're going to go to the other side, and as we can see, we have a second distributed load. So again, all I like to do personally is just put a nice dashed line representing the distributed load. We know that this one is kind of triangular, so I'm going to have it like that, and I'm going to fill it in with the force representing where it is. So we'll call this one F2. Nice and simple so far. This should be nice, easy marks for each and every one of you, which is great. Now the final thing, of course, you have to do in a free body diagram is you have to give dimensions. Alright, so that's going to be very important. So what I'm going to do is I'm just going to draw a nice line spanning the length of the beam, and we are going to go through and just draw all of the dimensions. And it's basically just copying the diagram above. So we have 1 meter, 4 meter, 1 meter, and then 3 meter. So 1 meter, 4 meter, 1 meter, 3 meter, and then we know that the height of this frame is also 3 meters. So I'm just going to put this here, 3 meters. And then one other thing that you should technically do is also describe the distances of the distributed load. So we know that for F1 here, this distance right here, since it's a rectangle, is going to be the midpoint of that rectangle, so 4 divided by 2, so we know that this is going to be 2 meters. And then for F1, since it's a triangle, we know that this is going to act at a distance of b over 3, or 1/3 of the base. So this will just be 3 divided by 3, or 1 meter. Now the last thing that we should technically do as well is we should describe what F1 and F2 are. So if we were to look at F1, we know that we can express it in terms of kilonewtons as a concentrated force just by simply taking the magnitude of the distributed load, in this case it's 20, and then multiplying it by the length it acts over. So in that case it's 4. So if we go 20 times 4, we end up with 80 kilonewtons. So I'm going to come down here, F1 is equal to 80 kilonewtons. Actually, what I'm going to do, just to really make sure that everyone understands where this came from, is let's just do the actual calculations. We had 20 kilonewtons per meter, and we're multiplying that by 4 meters. As we can see, even with the units, everything cancels nicely to obtain 80 kilonewtons. We're going to go over to the triangular distributed load, and it's going to be the same thing. We're just taking that area. So we're going to go 1/2, because it's a triangle, of 20 kilonewtons per meter times 3 meters. So as we can see, it's not too bad at all. I'm going to come down here. I'm going to say F2 is equal to 1/2, again, because it's a triangle, 20 kilonewtons per meter multiplied by 3 meters in this case. So 20 times 3 is 60, divided by 2, we should get 30 kilonewtons. Alright, so now if we were to look at our free body diagram, we basically have everything we need. If you're always wondering, hey Clayton, what is a good free body diagram? Well, you should be able to solve whatever the question is asking based on your free body diagram. So now it becomes, okay, how do we determine these support reactions? Typically, in the cases where you have these hinges, so again, if we were to look at our actual picture, we know that there's a hinge at D, there's a hinge at B, and then there's a hinge over at C. Typically, we would have to split the beam apart. But here's the trick. You don't have to do that if you already have enough equilibrium equations. We know from the theory that for any sort of free body diagram, we have 3 equilibrium equations. Sum of forces in x is 0, sum of forces in y is 0, and the summation of moments is also equal to 0. So we can technically solve for 3 unknowns. Remember, the number of equations is the number of unknowns. If we were to come down to our free body diagram down here, we actually only have 3 unknowns. We have ax, we have ay, and we have by. So technically we have everything, we have the capability of solving for these support reactions without having to separate the beam in any way. So that's kind of the first thing, and this is why it's good to do a free body diagram, because then it's very easy to determine if you need to split the beam up or anything like that. So I'm going to go right into solving for these reactions. I'm going to go down. I'm going to go summation of forces in the x direction. You can start off with whatever one you like. It doesn't really matter. We know for static equilibrium, this must be equal to 0. And if we were to just look at our beam, we actually only have two forces in the x direction. We have, and I'll highlight them, we have AX, and we have it pointing to the right, so it's going to be positive. Remember, that was just an assumed direction. And then if we look, we have an external load of 40 kilonewtons acting to the left. So I'm going to go down here and say, okay, we have AX minus 40, and those were our only two, and this has to be equal to 0. If we were to solve this equation, it's very easy to determine that AX has to be equal to 40 kilonewtons. And since we are assuming a direction, what I personally like to do is just add in an arrow showing the true direction. So we know that our assumption was correct, and AX is actually pointing to the right. So that was nice and easy. Now, for the second one, a lot of students like to go into some of the forces in the y direction is equal to 0. Personally, I avoid that one because if we were to look at the y direction, I'm just going to erase the highlighter for the first two. If we were to look at the y direction, we have both AY and BY. So even though we can create the equation, we're not really getting anywhere fast because we have two unknowns in one equation. So for my second equation, I always like to take the summation of moments, because if we were to take the summation of moments at point A, well, AY cancels. Or it doesn't really cancel, it creates no moment. So our only unknown in that equation would actually be BY. So I'm going to come down here, I'm going to say, okay, some of the moments around point A must be equal to 0. And then I'm just going to go through and I'm going to label all of my forces. So the first one to keep in mind, which could be really tricky to students, is going to be this concentrated moment. We have a concentrated moment of 20 kilonewton per meters, and that absolutely has to go into our equilibrium equation for moments. If we were to look at the direction, we can see that it is going clockwise, so this is actually going to be a negative moment. So we're going to have negative 20 to start us off, and then what I do is I basically just go left to right. So we start off with the negative 20. As I go through the beam, the next force that we have is going to be F1, and we know that F1 is 80 kilonewtons. So I'm going to come down here, we're going to put in the 80, and then we have to multiply by the moment arm, which is going to be that 1 meter plus 2 meters, so it's going to have a total of 3 meters. Come down here, 80 multiplied by 3, and then we have to consider the direction, of course. So if I were to hold my pencil at A, and I know I don't have the video camera, but you guys all know what I'm talking about, and I were to press down on my pencil, kind of on the right-hand side, as we can see, this starts to create a clockwise rotation. And we know that clockwise is negative, so this will in fact be negative. So that's going to be F1. I'm just going to erase the highlighting. The next one is going to be BY, and that's an unknown, so we're just going to have BY. And then we have to multiply it by that moment arm. And if we look up here, it's just going to be 1 plus 4 meters, so a total of 5 meters. Come down here, I'm going to put in 5. If we were to look at the kind of rotation BY creates, again, I'm just going to hold my pencil, and this time instead of pressing down, I'm going to press up, like we assumed for BY. And as we see, it creates a counterclockwise rotation. So we know that this is going to be a positive value. And then moving on, we can see that we also have F2. So F2 we already know is 30 kilonewtons. So I'm just going to come over here. I'm going to put 30. The moment arm is going to be 1 plus 4 plus 1 plus 1. So that should be 7. So there's a little bit of math involved, but not too bad. As we can see, this will also create a clockwise moment. So it's going to be negative. And then the other thing that a lot of students tend to forget, so please don't forget, is that this force up here, this 40 kilonewtons, that will also create a moment because it is offset from point A. So we're going to have the 40 kilonewtons, and its distance is going to be the 3 meters at the end. So I'm going to come down here, so we're going to have 40 times that 3 meters. And if we look, we have to just check the sign. So if I were to hold my pencil at A vertically at the bottom, and I were to push on it kind of directed left, as we can see, we are creating that counterclockwise rotation. So this will actually be positive. So positive, and that's it for all of our forces. And we know for true equilibrium, this has to be equal to 0. And as we're going to see, if you were to solve the equation, our only unknown is By. And if you solve it, you will determine By as 70 kilonewtons. And the assumed direction of upwards was actually correct, so I'm just going to put 70 kilonewtons upwards. And I'm actually just going to underline these in, let's say, blue, just to keep track of where our support reactions are. That's another little trick or tip, if you will, for the exam. Always highlight your final answers. If the professor or the TA or whoever's marking it can't see where your final answer is, well, chances are you're going to get some marks taken off. So please make sure you highlight your final answers. So I'm just going to erase all of the highlighting. I know it's pretty tedious for you watching the video, but I just want to make sure that everyone is following along as much as possible. So now that we have By, we can go summation of forces in the y direction to solve for Ay. So I'm going to go summation of forces in the y direction is equal to 0. Again, we couldn't do this before because we had two unknowns, but now we have everything we need. So just going, again, left to right, we have Ay minus F1. So I'm just going to kind of do this a little bit quicker because you are all so familiar with this now. Ay minus F1. Well, we said that F1 is equal to 80. And then again, just going left to right, we have plus By minus F2. So coming down here, we had plus By, and we know that By is actually 70. And then minus F2, which we said was equal to 30. And if I were to just kind of look to the end of my beam, there's nothing else, so we can actually solve for Ay. And we'll see that Ay is actually equal to 40 kilonewtons. And our assumption of upwards was also correct, so 40 kilonewtons upwards. So I know I dragged this on quite a bit. Again, I just want to make sure that everyone's following along. But if you were to do this in an exam, this would probably take you all of 2 seconds to do. So that's going to be the support reactions. The next part is what's going to trick everybody. And that's going to be part B here. And it says determine the forces of pins B and pin C on the beam. So I'm just going to erase kind of this purple. Actually, I'll erase all the highlighting right here. It wants the forces in these two pins. So we have B as well as C. And as we're going to see, this is actually going to become critical because if we don't have them, then part C, where we're asked to find the shear force diagram and the bending moment diagram, well, we can't really do too much because we don't have all of our forces. So here's the trick to those two members. And actually, I'm just going to go up and see their names. So let's first look at member, and I'm going to highlight it, BD. So this is going to be that vertical member. I'm just going to come right down here. I'm going to put in part B. And we are going to discuss this because once you get this trick, everything is actually easy street, which is good. That's what you want. Actually, I'm going to put this down a little bit. If we were to look at this member right here, and we know that it is pinned on both of the ends, well, we can basically conclude that there's going to be two forces acting on each end. A horizontal force as well as a vertical force. And again, there's going to be no moment because it is pinned at that end. So I'm just going to write it as such. So this should be trivial to you all. Now, one of the things that we can do, as you guys remember from force components, is if we have an x component and a y component, well, we can basically express those two forces as a single force. So what I'm going to do, I know that this is not the best colored, but I'm going to say if I have an x component and a y component, I can express these two forces as a single force as follows. So on both sides, I'm going to have it as follows. So now I'm going to erase our pink forces. That's not the eraser, that's the highlighter. So I'll get rid of that, I'll get rid of that. So now we have these two forces. Now, if we were to actually consider these two forces, we also have to keep in mind that our member here has to be in equilibrium. What does that mean? It means that the summation of forces in x must be equal to 0, summation of forces in the y must be equal to 0, and the summation of moments must be equal to 0. Now, if these two forces were equal and opposite, which is what we're assuming, so we're going to have F on one side, F on the other side, well, we can tell right away that both the x direction and the y direction are going to cancel. So the summation of forces in x and y, that's taken care of. The only problem that we have is the summation of moments. as we can see, if I were to draw a dashed line of these forces, kind of their line of action of these forces, they act at a distance. And we know that that distance is actually going to create a moment couple. So we can actually tell intuitively that these forces cannot possibly act in this manner. The only way for these two forces to actually satisfy moment equilibrium is the following scenario. So I'm just going to erase this really quick, and I'm going to show you is this scenario right here, where we have a force going upwards on one side, and we have a force going downwards on the other side. Now, of course, this can be opposite, where at the top of the beam we can have a force downwards, and at the bottom we can have a force upwards. But basically, this is going to be the only scenario, and I'm going to call this F. What was it? CD? I'm just going to make sure I got BD. BD, not CD. So let me just erase this. This is going to be BD. And we have FBD. Again, they could be opposite in direction. I'm just assuming that we have the following state. If we were to look at this particular scenario, the summation of forces in the y are indeed going to cancel. Summation of forces in the x is not a problem because there's no x component. But if we were to check, the summation of moments is actually equal to 0. If I were to consider a point right in the center of the beam, and I were to take my summation of moments, well, as we can see, both of these forces run through this point, so they're not going to create moment. If I were to move my point over here, again, both of these forces will now create moment, but they're going to be equal and opposite. So they're actually going to cancel out, which is nice. So that's the trick to these questions, is that if we have two forces on our member, and this is actually referred to as two force members, they actually have to act in a certain manner. So this was BD, and I'm just going to label BD so everyone knows what exactly I'm talking about. This was B, this was D. And we can do the same thing to member CD, so that L-shaped member, or yeah, CD. So we know that member CD looks something kind of like this. Again, I'm taking a long time with this, but you understand why I'm doing it. I just want to make sure that everybody is following along. Just like before, we know that at both ends of this member we have a horizontal and vertical force, but I'm going to treat them as just a single force like this. So we're going to have one force here, and we are going to have on the other side one force kind of over here. And then we have to apply the exact same principles that we did before, where we need to ensure that the summation of moment is 0 everywhere. Summation of forces is 0 both in the x and the y direction. And the only way that's possible, and again this goes back to two force members, is if the members have the same line of action. So what I'm going to do is I'm just going to erase both of these forces, and I have to ensure that they have the same line of action. So I'm going to draw a dashed line between these 2 points, like this, because the only way that these two forces don't create a moment is if they're both along this same line of action. So we're going to have a force like this, we're going to have a force like this, and I'm going to call this one FCD, and we're going to call this one FCD. They have to be equal and opposite in order for the summation of forces to be 0. But the nice thing here is this. We now know the inclination of these forces. If I were to go into my purple marker here, we know this inclination right here, because it's just going to be, the base is going to be the length of D, which we have as 4 meters. So 1 plus 3 is 4. Just making sure you guys know where I'm getting these numbers from. So we got 4 meters along the base. The height is going to be just 3 meters. So I'm going to have 3. And then we know that if we have 3 and 4 on our triangle, well then the other side must be equal to 5. Now you're saying, Clayton, who cares about this? Why exactly are we doing this? Well, if we were to come up to our structure now, and we were to actually analyze hinge D, well, we now know how to express member DC as a force. We know how to express member DB as a force, and we have that external load to our hinge of 40 kilonewtons. So this is actually going to be kind of reminiscent of trusses, where if I were to look at this hinge here, we know all the forces that act on it. So let's go back to red. We know that we have a horizontal force of 40 kilonewtons. This is actually going to go back to particle equilibrium. We know that there is a force from dB, which we have as pointed downwards in our current free body diagram. That may be incorrect, of course. This is just an assumption. So this is going to be FBD. And then we have basically a diagonal force from FDC. So this is why it was important to figure out that these were two force members, because now we know the orientation of all the forces. Actually, that would be the opposite. Oops. That would be the opposite direction of what I wanted. I write sideways, so it's kind of hard. I have to flip the iPad around each time I want to reorientate everything. We have FCD. So again, these were just assumed directions. We don't know if they're correct. And what's nice is we now know, what should we do? Blue. We know the inclination of FCD. So it's going to be 5 on this side. It's 3 high, and it's going to be 4. And from here, what we can actually do is we can just take particle equilibrium, because we have 2 equations and we actually only have 2 unknowns. So it's actually really nice for us. So I'm going to go over to red, and I'm going to go summation of forces in the x direction must be equal to 0. As we can see, we have 40 kilonewtons going to the left, so negative 40. And then we have a component of FCD going to the right. So we're going to go plus FCD. Again, it's going to the right, so it's going to be positive. And the component is just going to be the basically the horizontal over the hypotenuse. So 4 over 5. And as we can see, we can solve for this because this has to be equal to 0. So the force in hinge CD actually has to be equal to 50 kilonewtons. 50 kilonewtons. And the nice thing too is that our actual signs or assumption or assumed direction was correct. I don't know why I couldn't say that too much. All right, so I'm going to come down here. I'm going to say that we now have some of the forces in the y direction is equal to 0. So if we were to look here, we have BD going downwards. So we have negative FBD, and it's going strictly downwards, so the full force is going down. And then we have FCD also going downwards. So we're going to have minus FCD, and then multiplied basically by its vertical component, which is going to be 3 over 5. And this is going to be, of course, equal to 0. So from here, we can actually solve for BD, not CD. Because we know what FCD is. We just solved for it as 50. We can find that FBD is equal to 30 kilonewtons. And it's actually equal, it's the opposite direction that we assumed. It's actually going upwards in this particular diagram. So this is how we would actually solve for the forces in these hinges. Now what I'm going to do is I'm going to set it up so that the next question is actually a little bit nicer. I'm going to take all this over here, just like this. I'm going to copy it. I'm going to bring it down here. And I'm going to say that since we now know all of those forces in our hinges, we can actually eliminate those members from our free body diagram. So I'm going to get rid of the 40 kilonewtons. I'm going to get rid of this top part, same with the side parts, just like this. I'm going to get rid of that right there. I'm going to have to touch up my free body diagram for that distributed load because I erased some of it. So we know that we have this. But the nice thing that we have now is we now know how these forces actually act on our beam. So based on what we figured out, and I'll put it in pink. All right, we'll put it in pinks. Everyone likes pink. We know that in FBD we have 30 kilonewtons, and this will be going downwards. So this right here will be 30 kilonewtons. This will be on that hinge right there. And then at the far end, we have FCD, which was 50 kilonewtons, and we got the force right. So it's actually going to go kind of something like this. And this right here is going to be 50 kilonewtons. And if you want for completeness, of course, you should put the inclination of it. And we've already discussed that that's going to be 5, 3, and 4. So not too bad. So this is how you would deal with part B. And this is why it's important to know these steps, because if we didn't know that 30 kilonewtons or that 50 kilonewtons, well, we're going to have a really bad time, because if we were to look up, the next question is draw the basically the shear force diagram and the bending moment diagram. Now it also says, please clearly label your diagrams. And what it means by that is that you just have to label the values. You'll see a lot of students at the end of exam rushing, and they'll basically just draw a curve. They won't put any values or anything like that. And it may be a correct profile, but without those actual values, it's hard to award marks to students. So what I'm going to do is I'm actually just going to move this upwards a little bit so it doesn't get in the way. And I'm going to copy it because we are going to now draw the free body diagram, or sorry, the shear force diagram. The nice thing for us, and I'm going to do it down here because it's kind of separate from the rest, we have everything right here. What's nice for us is that we have everything that we need. So I'm going to erase a lot of these, and I'm actually going to even erase AY, BY, and I'm going to put in their actual values. I'm going to erase F2, of course. One key thing is when you're drawing shear force diagrams and bending moment, shear force, yeah, I said it right. When you're drawing shear force diagrams, it's important to actually have it as a distributed load rather than a point load. So for instance, I'm going to have 20 kilonewtons per meter here. On the purple side, it's also 20 kilonewtons per meter. We know our reaction forces. We said that AX was 40 kilonewtons. We said that AY was, I believe, 40 as well. We'll just go up and check. Yep, 40 kilonewtons. I don't know why I can't speak. 40 kilonewtons. We know that this is 70 kilonewtons. And if we were to look at our diagram here, it's actually nice because we have every piece of information. There is no unknowns. So we're going to do the easy method for the shear force diagram. So what I'm going to do is I'm just going to draw a nice vertical axis, something like this. And we're going to start off with shear force. So it's going to run kind of the span of the page. Typically in exams, they'll provide you with these axes, so you don't have to worry about it too much, drawing it. Unfortunately, you have to sit here and watch me draw. So right here, I'm just going to put that this is going to be our shear, and it's going to have units of kilonewtons. As we're going to see, drawing these diagrams, if they don't ask for a specific method, is really simple. Because we are going to utilize the property that, and I'll put it kind of in pink on the side here, that the change in shear between 2 points is actually just equal to the area of our distributed load, which I call Q. You can call it whatever you want. And the other thing to keep in mind, of course, is that if we ever were to have a point load, it's going to either bring our shear up or it's going to bring our shear down. So all we actually really need to do in this scenario is just go left to right. If we were to start off at the very left, and again, shear force is mainly concerned with vertical forces, we can see that right at the beginning we have a 40 kilonewton force popping our shear diagram upwards. This comes from the reaction at A. So we know that we are actually going to go up kind of by a magnitude of 40 kilonewtons. So this is how we start our shear diagram. And then the next part is you just want to go from left to right, and the only changes that will happen is if you have a distributed load or you have a point load. So if we were to look at our diagram here, and let's label these points as follows. Let's say we have A, B, C, D, and E. I know that this is not how they are shown in the diagram, but this is how we are going to do it. If we were to look at our first segment from A to B, we have no point loads and we have no distributed loads. So what I'm actually going to do to hopefully kind of show what areas I'm talking about is let's just create little segments. Let's decrease the line thickness too. That was a bit much. So hopefully this will help. If not, I'm sorry for wasting all your time. I'm trying my best. I just want to make sure that everybody knows which segments I'm referring to at any given point. So we have these segments. So again, for our first one here, now I have no idea if the line width is correct. Let's take a peek. All right, that looks the same. So for our first segment, A to B, again, we have no distributed load and we have no point load. So we know that the shear diagram is actually not going to change. It's going to remain constant. So that's still 40. I know that I actually drew it kind of inclined up a bit. This is constant. It does not change. That looks a little bit better. Now, once we get into segment BC, we actually see that something's going to have to change because we now have that distributed load of 20 kilonewtons per meter. That's when we actually have to go to our formula over here. So I'm going to erase it, and we're just going to come down here, and we can say that the change in shear between these 2 points, so BC, this is equal to the area of that distributed load. So we have 20 kilonewtons per meter, and the thing to keep in mind is this is actually going downwards. So we'd have technically negative 20, because again it's going downwards, and then the base of this rectangle is 4 meters. So negative 20 times 4, we throw that in, we get negative 80. So all this means is that the change in shear between point B and point C is going to be negative 80. And this is nice because if we know the shear at B, well then we can calculate the shear at C. So the shear at C is going to be equal to the shear at B plus the change in shear between these 2 points, B, C. We know the shear at, the shear at B is 40. We get that right from our diagram. So we're going to have 40 minus 80, which is going to be equal to negative 40. Now, we know basically now that the shear at C is going to be negative 40. So what I can do is I can draw a dot. We know that at this point right here, our shear, I'm just going to have to move up a bit so I can write comfortably, is going to be negative 40. The last thing that you need to do is you need to show kind of what is the profile of the line. Now here's the nice trick. The shear will always be one order up than the distributed load. So as we can see, we currently have a constant distributed load, which means that we are going to have a linear shear profile. So what I can do is I can actually just start at B, and I'm just going to draw a linear line over there down to C. We know that this must be our actual shear profile. One thing that they're going to ask for is going to be now this distance right here. What is the distance where our shear actually hits 0? And as we can see intuitively, since it goes from 40 to negative 40 over a distance of 4 meters, we know intuitively that this is going to be, of course, 2 meters. But the question is if you don't know that intuitively, how can we solve for it? Well, basically what we do is we use the same formula that we just did, and I'll do this one in red so you know what I'm talking about. And we can say, okay, if I know the shear at point B here, which is 40, and I know the shear here, which is 0, then I can tell the change in shear between these 2 points. So I'm going to say that the change in shear between point B and where our shear is equal to 0, we know that this is equal to negative 40. Right? It makes sense. We dropped 40 kilonewtons to get to 0. Now we also know that this right here is equal to the area of our distributed load. So we're going to go up here, and as we can see, the height of the distributed load, it's always going to be constant. It's going to be that 20 kilonewtons per meter. So this is going to be equal to negative 20, and then we need to figure out the base of the distributed load. So if I were to come up here, I'm basically trying to find this distance right here, this distance D, where this area would give me negative 40. So this distance right here would just be D, we don't know. And as we can see, we can solve for D, and we can find that D is actually equal to 2 meters. So that's how you'd figure it out if you didn't already know, but I'm sure that a lot of you guys already know how to do that. So I'm just going to erase the mark there, and we are going to continue on. Again, just using the same things that we did before. Now, if we were to look at point C, we have 2 point loads. All right, we have 70 kilonewtons upwards, and we have 30 kilonewtons downwards. The key thing is the actual jump is just going to be basically the magnitude of the resultant. So if we have 70 up and 30 down, we know that overall we actually have 40 kilonewtons going upwards. So in our shear diagram, we are jumping up by 40 kilonewtons. And this will actually take us right to 0. Okay, again, it's just 70 minus 30 is 40. That's how we get it. If we were to look at the next segment between D and C, we actually have nothing going on. We have no point load, and we have no distributed load. So we know that this is actually going to be constant through these 2 points. Now to finish us off is we have a triangular distributed load. And it's actually not going to be too bad because again, the change in shear between these 2 points, which is D and E, is going to be the area of that distributed load. So the change in shear between these 2 points, which in this case I have is D and E, so point D, point E, is going to be the area of that distributed load, which is a triangle. So we have 1/2. Its height was -20, and then its distance, I believe, is 3 meters. Yep, 3 meters. So if we were to calculate this, 20 times 3 is -60. Then you 1/2 that, of course, you get -30. So -30. Now again, this will allow us to solve for the shear at point E because we know the shear at D. So the shear at E is going to be the shear at D plus the change in shear between these 2 points, so it'd be DE. We know that the shear at D from our diagram starts at 0, and then we're basically subtracting 30, and we get this is equal to -30. So I'm going to come up here, I'm going to say, okay, at this point over here, we know that our shear has to be -30. So I'm just going to put another mark on my axis, -30. And how do we tell the profile? Well, again, our shear force will always be 1 order up than our distributed load. So we know that since our distributed load is linear, our shear force diagram actually must be quadratic. Now, here's the one problem that, again, students are going to have. We can either have this scenario, or we can have this scenario, concave up or concave down. Both of these are actually quadratic. This is when you have to utilize one other aspect, and that is this. The value of our distributed load is actually equal to the slope of our shear force diagram. So if we were to look at the left-hand side of this distributed load, which I now highlighted, we know that our slope is -20. So in our diagram, we must have a slope of -20. If we were to look at the other side, we know that our distributed load at point E is 0. This basically means that our slope at point E must be equal to 0. So it must be horizontal. As we can see, if we were to consider this aspect, the only possible curve that would fit this scenario is going to be that bottom one. So we know it has to actually look like this. So I'm just going to erase these. You guys know what I'm talking about. Nice and easy. Now, of course, we know that our shear force diagram must end at 0. And if we were to look, we have that 50 kilonewtons there. And if we were to only consider the vertical component, so I'll just put a little arrow to the side. If we were to consider the vertical component, well, it's going to be 50 times 3/5, which is equal to 30. And as we can see in our shear force diagram, if we jump up by 30, we end back at 0. So this would be how we figure out our shear force diagram. Now, of course, if you wanted to be, I don't know the word, nice, I guess. You guys don't want to be nice to the markers. I already know it. You would kind of shade it in or something like this to show everybody what exactly it is, but I'm not going to do that. You guys already know how to do that if you guys want. Now, the nice thing from this is if we can look at this diagram now, we already know that our maximum shear, which is related to question D, which I'm just going to call V max, well, this is going to be equal to 40 kilonewtons. That's pretty easy to see. We just had to look at our diagram. And that's going to be the shear force diagram. Now, the next thing that they wanted, and I'll just put this right here. This would be part C. The next thing that they wanted was the bending moment diagram. And for the bending moment diagram, we actually need both our free body diagram as well as our shear force diagram. So what I'm going to do is I'm just going to copy this, and we are going to do it fresh on a new slide, or a new page, I guess. Come down here. We are going to paste it right here, and then now below I'm going to now draw another set of axes for our bending moment diagram. So something like this. It's going to run, usually the bending moment's all positive, so I'm just going to have it kind of offset. We know that this is going to be the distance along our beam in meters. Put these axes right here. And again, this axis is going to be for our moment, which is going to have units of kilonewtons per meter. Moment. Nice and simple. So what we'll do, and actually I guess I will shade it in because it's kind of driving me crazy. We'll shade it in because this is going to help us for the moment diagram. Not too bad. I know you guys are already getting bored. No one's watching the video this long. If you're still here, I guess thank you. Oop, I'm going to make this a little bit nicer. And we are going to do our bending moment diagram in purple. Now the nice thing about the bending moment diagram, and I don't know why I zoomed in, is it follows the exact same concepts as our shear diagram did. Remember that for shear, it was the area under the distributed load. Well, for moment, it's actually going to be the area under our shear force diagram. Now, a lot of students are going to say, well, Clayton, if it's just the area under shear, why did you need to draw this free body diagram? Couldn't you have just drawn the shear diagram and go from there? Well, I could have, but here's the one problem. Just like in the shear diagram, where if we have a concentrated load, we have to jump up or down, in our moment diagram, if we have a concentrated moment, well, then we also have to jump up or down. And if we were to look at point A, we have a concentrated moment of 20 kilonewtons per meter. So what would typically happen is students would just refer to the shear diagram and then they would get everything wrong. You have no idea how many times I've actually seen that happen. So it's important to look at our actual diagram and we can say, okay, right at the beginning, we have a jump in moment of 20 kilonewtons per meter. Now, it's going to get a little bit tricky because if we had a force going downwards, we would drop our shear downwards. But for moments, it's actually the opposite. And this is just due to sign convention. And what I mean by this is if we were to look at that 20 kilonewton meter, we can actually see that that is a negative moment. As we can see, again, negative moment. But a negative moment in our shear force diagram actually pops our diagram upwards. So we know that, well, I don't know why it's doing that. We know that we are actually going to have a slight jump to start our moment diagram of 20. And again, this comes from that concentrated moment right at the beginning. If you were to not consider that free body diagram, well, you wouldn't have that jump and then everything would go to garbage really quick. Now, the next part is actually pretty nice because all we are doing now that we've taken care of those concentrated moments is again just looking at the shear force diagram because we know that the change in moment is going to be the area of our shear force diagram. So what I'm going to do is I'm going to come down here and I'm going to say, okay, we're at point A and the change in moment between point A and point B is going to be the area of our shear force diagram in these 2 points. So I'm going to go to highlighter here just so you guys can see. So our first area would be this area right here. So as we can see, the height is going to be 40 and the base is going to be 1 meter. So I'm going to keep erasing it or else I'm just going to have a real mess on my hands. So again, we know it's going to be 40 multiplied by 1. So this is going to be equal to 40. So therefore, we can figure out our moment at B because it's going to be our moment at A plus the change in moment between these 2 points. You don't have to write this down all the time. Again, I just want to make sure everybody knows how to do this completely. So the moment at A, well, we know that that is going to be 20 kilonewton meters. The change in moment, we already said, was 40. So we now know that the moment at B has to be equal to 60. So I'm going to come up here and I'm going to say, okay, my moment at B has to be 60. So far, not too bad. Now, the key thing, again, of course, is going to be what is the profile between these 2 lines? Well, again, moment is actually going to be 1 order up in shear. So since our shear is constant between these 2 points, for moment, it's actually going to be linear. It's going to look something like that. Not too bad. Now, typically, what you should do is you should just write a little symbol or something. For me, I put L for linear, just to make sure that the marker understands what exactly the line is. This won't really come into play for linear lines, but for quadratic and cubic lines, they look similar, so it's good to make some sort of distinction between them. So the next part here is going to be, okay, what is going to be the change in moment between point B and I'll put point 0, which is going to be that intercept right there. So basically, if I were to look at the area, I'm now considering this area right here. As we can see, it's a triangle, so I'm going to go 1/2 of the height, which is 40, times the base, which is 2, so not too bad at all. So I'm going to say the change in moment between B and 0 is going to be 1/2, again, triangle. The height is 40, and the base was 2, so we're going to get 80 divided by 2, so this is going to be 40. I'm not going to do the moment there, because once we find the change, you guys can all do the simple calculations. So we know at this point right here, which I'll do a dashed line to kind of show everybody what I mean. For this point right here, we are going to see that our moment goes up by 40, so we're going to go from 60 all the way into 100. Again, 60 plus 40. And if we were to look at the order, since our shear is linear, we now know that this must be quadratic. So we're going to say, okay, it's going to have this profile like this. Now again, some of you may be saying, well, Clayton, how come it's not this profile? And what happens is that the slope of the moment is equal to our value of shear. So if we were to look at our shear, we have a positive slope starting, and then we go to a slope of 0. All right, so we start off with a positive slope, and then we go to a slope of 0. So that's how I know that it is actually the first curve and not the second curve. Now what's nice is we can just continue on. So now that I have the shear at point 0, we can find the shear from O to C. I'm just going to highlight it right here. We can now find this shear right here. And as we're going to see, it's going to be 1/2 base times height because it's a triangle. So it's going to be 1/2 of negative 40 times 2 meters. So let's come down here. The change in moment between 0 to C is equal to 1/2. And this is key. If our shear is negative, we have to input it as negative. So that would be the height times the base, 2 meters. And we get that this is equal to negative 40. So if we come back up here, we're at 100, but now we know that we must drop back down to 60. So we're going to drop back down to this point. And again, if we were to look at our shear force diagram, we're starting off with a slope of 0, and we are going to a negative slope. So the curve that would correspond to this would look something kind of like this. Again, I'm not an artist, neither are you guys, and we don't expect you to be. So this would actually be considered good enough. The thing that you would want to do is you just want to put a Q for quadratic, quadratic, just so that the marker knows what exactly you're trying to draw, because again, we're not really artists. All right, so if we were to look at the next part, which is from C to D, as we can see, we actually have no area under our shear force diagram. So we know that in terms of moment, the change in moment would actually just be 0. Nothing happens between these 2 points. So we're just going to go on like this. And then for our last part, we need to find the change in moment between this last section here. Now there's kind of a trick to this. If we were to look at D and E, we were able to find the area of the distributed load to find shear. Now for moment, it gets a little bit harder because keep in mind that this formula, or this curve, is quadratic. So it's kind of hard to find the area under a quadratic curve. So this is when you are going to cheese it just a little bit. Just like shear, you know that our moment diagram must end at 0. The only thing that would stop it is that if we had a concentrated moment at E. As we can see, we don't have any concentrated moment. So we know intuitively that our moment at the last point here, which is point E, this has to actually be equal to 0. It's the only way our beam stays in equilibrium. So we can just say, okay, I know the moment between these 2 points. All I need to do is draw the curve. And again, the curve, since this is the shear is quadratic, the curve is going to be cubic. Now the question becomes is, okay, well, what are the slopes? Again, all we have to do is look at our shear force diagram. We start off with a slope of 0, and we go until basically we have a negative slope. So we know that our slope has to look something kind of like this. Again, not an artist. You guys aren't either, but that's all good. Actually, I shouldn't say that because students have been sending me their art, and yes, they are definitely artists. I'm just not an artist. And we know that since the shear is quadratic, this has to be cubic. So something like that. And then what's nice from here is we can tell intuitively from our diagram that our maximum moment has to be equal to 100 kilonewtons per meter. Or not per meter, 100 kilonewton meters. So 100 kilonewton meters. And that's it. Because once you have the diagrams, you can easily answer part D, which was, if I were to scroll up here, determine the maximum shear force and maximum bending moment in the beam. We did that. We are good to go. So that's it. That's it for this question. I know it's a pretty long question. I don't even know what my recording time is at. Probably about an hour. Realistically, you should be aiming to solve these questions in about half an hour. I did everything in painstaking detail. Like, for instance, I think I spent, 15 minutes on support reactions? Realistically, that would take you guys, I don't know, 3 minutes, 4 minutes. So you can definitely solve this faster. If you are getting sick of me dragging this on, I'm sorry. It's not what I want to do. I just want to explain every step in detail so that no one gets lost. Because if I were to, let's say, skip a description of a certain step, well, everything after that's not going to make sense. So it's pretty critical that I do a good job of that. But yeah, that's it for this question. So I want to thank you all for listening. I hope it was able to help somewhat, and I will see you guys in the next example video.